Okay, welcome to Data Mining course. In this lectures, we're going to discuss about association analysis, the basic concepts, and algorithms. This is our lecture number 6. So first, we start with association rules. A data mining association algorithm normally identify patterns in data sets. For example, items a customer often purchases together at a grocery store, or links on a website upon which a customer clicks before making a purchase, or snacks a fan purchases together at a ball game. So again, the goal of association rules is to find a patterns in a data set. And we're going to start with an example here. So here we have an example of a grocery store, 5 transactions. Each transaction is what a customer purchases. So our goal here is to generate an association rules, such as what is the possibility that if a customer buy a diaper, he will also buy a beer. Or when a customer buy a milk and a bread, he will also buy eggs and Coke. Or when a customer buy a beer, bread, he also buy a milk. Normally, this is implication. So on our left side, the diaper is called the antecedent. And on the right side, it's called the consequent. And the arrow to the right means implication. So here we say implication means co-occurrence. They occur, but not causality. So for example, we will not say that anytime a customer go to a supermarket, if he buy a diaper, he must buy a beer. That's not a causality. So again, that's our database here with 5 items. 5 transactions, and the items are 6 items. So we start with the definitions of some few terminologies. So first, what is an item set? We say an item set is a collection of one or more items. An example will be a milk, bread, and diaper. So a milk, bread, and diaper will be 3 item sets because we have 3 items. So a K item set means an item that contains K items. Next, we go to the support count. So support count is the total tally of an item set in a database system. So example here, we have a frequency of occurrence of an item set. In our database here, milk, bread, and diapers appears only twice, which means only 2 transactions out of the 5 transactions, we have milk, bread, diaper together. So that will be our support count. Then we have support. Support will be the fraction of transaction that contain an item set. So since milk, bread, and diaper appear solely twice, we know the total transaction is 5. So 2 transactions have milk, bread, and diapers. So the support will be 2 divided by the total transaction, which is 5. We also have the term frequent item set. The key word is frequent. We know what is an item set. It can be a collection of one or more items, but frequent item set means an item set whose support is greater than the minimal support threshold or equal. So what we mean is that, for example, here we're able to find the support for milk, bread, diaper to be 2 by 5, which will be 0.4. Now, if the minimum support threshold is given to be 0.5, then milk, bread, diaper is not a frequent item set. But if it's 0.2 or 0.3 and its support is 0.4, which means at least is greater or equal to the minimum support threshold, So we will say make bread and diaper is a frequent item set. So we start with the definition. Association rule normally goes with an implication expression of the form X implies to Y. X and Y are the item set. Sometimes we refer X, which is on the left side, to be antecedent, and Y to the right side is called a consequent. So an example here, we have a milk diaper implies to beer. So milk and diaper is our antecedent and beer is our consequent. So here, in order to test this rule, we need to find the support and also the confidence and make sure the support and the confidence is at least equal to the minimal threshold value. So we need to evaluate our rule. So rule evaluation metrics, we need to find the support. So the support will be the fraction of transactions that contain both X and Y, which means I'll look at my database system and I'll look for milk, diaper, and beer, how many times they appear is 2. Then I'll divide by the total transaction in the database system, which is 5, which means I'm looking for the fraction or percentage of the milk, diaper, and beer appearance. Now, next is the confidence, which is very important too. So anytime we are evaluating the rules, we need to find both the support and confidence. Confidence normally will measure how often items in Y appears in a transaction that contains X. This means I'm going to look at my database, how many times milk, diaper, and beer appears. Then I'll divide by how many times only milk and diaper appears. Because here we are looking for the measure of how often items in Y, which is beer, appear in the transaction that contains also X, which is milk and diaper. So we're going to find how many times milk, diaper, and beer appears divided by how many times milk and diaper. So support gives us the fraction of the transaction that contain both X and Y, which means contain both milk, diaper, and beer. Whereas confidence measure how often items, which is the beer, appear in the transaction that contains milk and diaper. So that's the formal example here. So we have the milk, diaper, and beer. We want to again evaluate this rule. So the support will be the count of milk, diaper, beer divided by the total transaction, which gives us 0.4. Then the confidence, which is C, will be the count of milk, diaper, and beer, which is 2, divided by the count of only milk and diaper. Because here we are looking for how many or how often beer appears in milk and diaper, the transaction. So it's 2 divided by 3. Again, we look at the database. Milk and diaper appear 3 times. Then milk and diaper beer appear twice. So if these 2 support and confidence values are equal to their minimal threshold or greater, then we say we are keeping the rule is valid. So again, given a set of transaction T in a database system, the goal of association rule mining is to find all the rules having a support that is at least equal or greater than the minimal support threshold. Also, the confidence should be greater or equal to the minimal confidence threshold. Now, how do we generate these rules? We can use what we call the brute force approach. Brute force approach, again, before we start, it's not good at all. It's very, very expensive computationally, and it takes a lot of time. Because if, for example, we have 5 items, we want to generate all the possible rules in the 5 items. We don't care whether the items is frequent item set or non-frequent item set. Our goal always is to remove the non-frequent item set. Then we leave only the item set that are frequent. Then we generate the rules. So with the brute force approach, it is the same concept in data structure when an algorithm. In algorithm, when we have a brute force algorithm, it means we are going to try all the possible way of solving a specific problem. Then we are going to select the best and shortest method. So this means the brute force approach, we need to list all the possible association rules. Then we are going to compute the support and confidence for each rule. Then we prune rules that fail the minimal support and minimal confidence thresholds. So the rules that doesn't meet the minimal support or minimal confidence, we are going to remove it. So the brute force, again, brute force, why we say so expensive or computational prohibitive, because first we generate all the possible rules. Sometimes the rules are very many. Based on the number of items, the rules may increase exponentially. So if it's 3, 2 to the power 3, 10, 2 to the power, so increase exponentially. So brute force, we are going to generate all the rules first before we remove all the rules that fails to meet the minimal support and minimal confidence threshold. So the measure of the performance of our association rule, we say the confidence. Again, the confidence is the percent of antecedent transactions that also have consequent item sets. We're also going to talk about a lift. A lift is normally the transactions with consequent as percent of all transactions. So normally the lift ratio shows how effective the rule is in finding the consequence. That's useful in finding a particular consequence is very important. And how we find the lift is always the ratio of the support over the confidence. So here we say if a lift is greater than 1, it indicates a rule that is useful in finding consequent item set. That is more useful than just selecting the transaction randomly. Support also always measure the overall impact because that's the fraction of the item set in the whole database system. Also, confidence show the rate at which consequence will be found. This is useful in learning the cost of promotion. Now, this is our database again with 5 transactions. We generate some few rules. So if we are using the brute force, if we have 3 items, we're going to generate all these rules. So you can see here we have milk, diaper, and beer. Next, milk diaper was the antecedent. Next, milk beer was at antecedent. Next, diaper beer. So we generate all the possible rules. Then we find the support and the confidence. Support always will be the same because support is the fraction of items that appears in the item set. So the always is milk, diaper, beer. Even we change the positions, but it's still the same 3 items. So the support will be the same. Confidence will change because the antecedent values may change. For example, here, if I'm looking for confidence, it will be beer, milk, diaper, how many times they appear? 2. Divided by how many times beer appear because my consequent is only beer. And in this case, beer will be 1, 2, 3. So we have 3 beer. Then with diaper, milk, beer, I'll count how many diaper we have. We have 1, 2, 3, and 4. So which means we divide 2 by 4. Again, the milk, diaper, beer, all the 3 items are purely 2. So when we divide 2 by 4, we get 0.5. The B appeared 3 times, so we divide 2 by 3, we get 0.67. DAP and B also appeared 3 times, we divide 3 by. So again, what we are trying to say is that the confidence always may change, but support is always the same. So that's the observation here. All the above rows are binary partition of the same item set. We have make, DAP, and B. Binary means 2. The partition here means we have antecedent and consequent is 2. The rules originating from the same item set have identical support. Since the item set are the same 3 item sets, the support will be the same, but can have a different confidence. So again, the confidence may change. Now, minor association rule, there's 2 steps approach. First, frequent item set generation. So we are going to generate all the item sets whose support is greater than or equal to the minimum support threshold. Then the rule generation, we're going to generate the high confidence rules from each frequent item set, where each rule is a binary partition of the frequent item set. So frequent item set generation is still computationally expensive. But here we have to generate frequent item set generation. We need to generate all the item sets whose support is greater than or equal to minimum support. Then we also need to generate high confidence rule from each frequent item set. So that's the brute force approach. We say that each item set is a candidate frequent item set. When we go through Apriori algorithm, now some of the item sets will not be frequent item sets. So we are going to reduce the rule. So with the brute force, as we said earlier, this is computationally expensive because we consider all the item set as a candidate frequent item set. So now we're going to count the support of each candidate by scanning the database. Then we're going to match each transaction against every candidate. So because of that, now our big O notation will be N times MW. M will be 2 to the power D. D is the number of items, or in this case, attributes, item set. So the possible rules we can generate. So here we say, given D unique items, the total number of items set will be 2 to the power D. Then the total number of possible association will be 3 to the power D minus 2 to the power D plus 1 plus 1. So for example, if D is 6, which means we have 6 unique items, then the possible rule we are going to generate to be 602 rules, which was our example that we saw with the 5 transactions. The number of items, again, is 6. Now, we need to find some strategy to reduce the number of candidates, especially if the candidate is not a frequent item set, we want to remove it. So we complete the search, M equal to 2 to the power D. Then we use the pruning techniques to reduce the M. So we're going to prune all the item set that are not frequent. So Apriori algorithm will tell us that if an item set is not frequent, then its subset also, they are not going to be frequent. So we are going to prune all of them out. Next, we can also reduce the number of transactions N. So here we reduce size of N as the size of item set, as the size of item set increases. Here we are going to use the DHP and vertical based mining algorithm. We're going to discuss this more detail in our next lecture. Also, we're going to reduce the number of comparisons. Here we are going to use efficient data structure to store the candidates or transactions. We can use the hash data structure, which we discussed in a data structure course. And also no need to match every candidate against every transaction. So the strategy again is to reduce the computational speed or the power. So reducing the number of candidates, we use what we call the Apriori Principles. We are going to use the waker again to implement this concept. And also later in the class, we are going to use the R. The R system also have a package, the R package for association rule, which is called the A rules package. It has the Apriori package. So if an item set is frequent, then all of its subset must also be frequent. That's what Apriori rule stated. So Apriori principle holds due to the following property of the support measure. So all X and Y, which is the antecedent and consequent, states here that if X is the subset of Y, then support of X should be greater than or equal to the support of Y. So support of an item set never exceed the support of a subset. So Y cannot exceed the support of X. And this is what we know as anti-monotone property of support. So example is given here. We have first, we start with single items, then the combination of them. You see that the combination is the same A, B, C, D. We have 5 item sets. The 2 item sets, possible combinations. Then when there are 3 possible combinations, then 5th means only 1 item because we have 5 items. So 1 item. Now, if we are doing Apriori, the first thing we need to look for is the infrequent item set that is not frequent, then we prune it out. But if we are not using Apriori, then we need to generate all the possible rules for all the items here. So here, for example, we say AB is infrequent. So you can see that all the subset of AB, which is ABC, ABD, ABE, then ABE is ABC, all will be prone. Because AB, these are all its subsets. So if AB is infrequent, then all the subsets will also be infrequent. And this is the Apriori principles. So let's see this example illustrating the Apriori principles. Again, we are going back to our database system where we have 5 transactions and 6 items. The first, our table we use for the market basket. Again, let's go back to the table. Make sure so I'm using this database system here, the table. We have 5 transactions, but if you count all the items here, it's 6 unique items. We have bread, milk, diaper, beer, eggs, and Coke. So there are 6. The rest is repetition. So that's why in Apriori, you see first we get the items set that are 1 each. So all the 6 items. Now we look at our database. How many times bread up? They will not appear more than 5, but because remember we have only 5 transactions. So if the item appear in all the transactions, they need to be 5. So here we have bread appear 4 times, 4 different transactions. Coke is 2, milk is 4, beer is 3, diaper is 4, egg is 1. But our minimum support threshold is 3. So which means any item set that the support is less than 3, we are going to remove it. So this means Coke and egg will be removed. Now we have 4 items now. We can see that we can generate lesser rule now or lesser item sets. If it's 6, we generate more item set for 2. So now we have combination of bread and milk, bread and diaper, bread and beer, milk and beer. So this is the possible item. Then again, we check our database. How many times each item appears? We saw that bread and beer appears twice, milk and beer appear twice. So we are going to remove the two. And the rest at least meet the minimum support threshold, which is 3. So next we continue. We have bread, milk, and diaper, and beer. So we are going to do the possible combinations, and the list keep going. So this means if this is 3, the rest is less than 3, we prune it, and this will be our rules that we generate. So that's the apron algorithm. As we saw the example, the first thing we have to start with 1 item set. So we let k equal to 1. Then we are going to generate the frequent item set for the length of 1 when k is 1, which that's what we did. The items that didn't meet the minimum support threshold, which means it's not frequent, we remove it. Then we move on, increase the k to 2. So here we say repeat until no new frequent item set are identified. Then we generate the length k plus 1. So we move to 2. And we do the same steps again. So we are going to prune the candidate item set that contains subset of a length k or less, which are not frequent or is infrequent. So we remove that. Count the support of each candidate by scanning the database. Then we remove or eliminate the candidates that are infrequent, leaving only those that are frequent. So reducing the number of comparison is the main goal here, which is the concept of apron algorithm. So candidate counting here, we say we're going to scan the database of transactions to determine the support of each candidate item set. That's to determine the support. So if the support is less than the threshold, we are going to remove it. If it's equal or greater, then it's an frequent item set, we keep it. So to reduce the number of comparisons, store the candidates in a hash structure. So here we can use the data structure, hash data structure to store the candidates, that's the frequency. So again, the concept here is to be able to reduce the number of comparisons, and we may go detail in our next lectures. So instead of matching each transaction against every candidate, we only match it against the candidates that contain in the hash buckets, because the candidates in the hash bucket are frequent candidates. So this is the diagram showing where we have our hash structure, the buckets, and the keys. So any frequent item set, again, we store it in the hash buckets. So the factors that affect the complexity. First, of course, the choice of minimum support threshold. If the minimum support threshold is very low, we are going to generate a lot of rules. So lowering the support threshold results in more frequent item sets. This also may increase the number of candidates and also mass length of frequent item sets. We know in computation, especially algorithm, the goal is for the algorithm to make decisions very fast and consume less memory or resources. So dimensionality also is very important. Dimensionality means the number of items. If the number of items increase, of course, that will make us generate more rules also. So more space is needed to store support count of each item. So memory usage. And if the number of frequent items also increase, both the computation, that is the speed, and also the input-output cost may increase, including the memory. We also need to consider the size of the database. Since Apron makes multiple passes, the runtime of algorithm may increase with the number of transactions. And the average transaction width, which is the transaction width, increases with denser data sets. And this also may increase the maximum length of the frequent item set, and also the transversals of hash tree. The number of subsets in the transaction increases with its width. And we may go detail more about the concept of using the hash tree in association. So that will be the conclusion of our lectures on association algorithm, the basic concept. And again, in Wake Up, we are going to use the Apriori algorithm to implement. And later in the course, we are going to use the R. So again, wish everybody the best. Thank you.